I have started recording the class. Today, my target is to finish Poisson regression. Poisson regression. But in order to finish this whole part, I have to go systematically from how the linear regressions come into an existence and what are the other components so that we can use these regressions. Okay, so there are 5-6 different topics I'm going to discuss to finish this regression, Poisson regression. First one, I want to discuss linear regression. Linear regression. Okay, so everyone know this is the line, this is the equation of a straight line. Okay, this is the equation of a straight line, and equation of a straight line and those all geometry was developed by the Euclidean geometry. Remember, his name is Euclid. Okay, I think Euclid, L-I-D. Euclid, he was a Greek. He was a Greek, and 300 BC, he was born in Alexandria, Egypt, and he was called the founder or the Tsar of geometry. Okay, so this is the equation of a straight line, the geometry. This was developed more than like 2000 years ago. Okay, this is the equation of a straight line. In 1805, Galton, he added a arrow term with this equation. Arrow term with this equation, and he called it as a model. Okay, in 1805, he added arrow term in this model, in this equation, and he called as a linear regression model. Linear regression model, he called it. So EI has certain properties. So this is called random error. It has certain properties or some properties. EI called the random error, which has some properties. So what is the properties? The mean of error equal to 0 and variance of error equal to sigma square. Sigma square. Okay, this is one important thing, and this yi he called as a response variable or dependent variable, dv, response variable or dependent variable. Okay, the xi is called the independent variable. It is called regressor. It is called explanatory variable. It is also called predictor variable. Xi. Beta 0 is known as the intercept, and beta 1 is known as the slope or rate or change of rate. something like that, whatever you want to say. Okay. So there are some assumption in this. Yi's are independent. Yi's are independent. So that means one yi value is independent from the next yi value. So there is no correlation between these yi's. When there is a correlation among yi's, then we have to use time series model known as the autoregressive model. Okay, so yi are independent. And then like covariance of xi and ei equal to 0. So there is no correlation between xi and yi. So these are the assumptions are considered by Galton 1805, and he said this linear equation now becomes linear regression model. Okay, clear, right?
The last covariance of xi
And ei. So that means ei and xi has no correlation. Okay, there is no correlation. They are independent. More specifically, ei and xi are independent. So it is written also like this way: ei independent of xi. They do not depend on each other. So this is the linear model was given. He added just an arrow term. Okay, this arrow term. This arrow term is also known as the beyond human control. Okay, ei equal to beyond human control. For example, in a production process, some of the finished product, for example, in peanut butter factory, okay, some of the peanut butter is mixed up with the machineries, right? Some of the crops of the farmer is destroyed by the birds, right? By insect, right? So which farmer cannot control. Similarly, when a dairy farmer milk the cows, when he put the machine, some of the machines misplaced and some of the cow milk is wasted, right? So error term beyond human control. The minimum the error is, the maximum the production is. Clear, right? So the purpose is to minimize the error. Okay, the purpose is to minimize the error. Yi and xi must be given. Yi and xi are given, which are data. Purpose is to estimate. Purpose is to estimate beta 0 and beta 1. Clear, right? Purpose is to estimate beta 0 and beta 1. Clear? Clear, right? Now you know how to solve this problem. 2x1 plus 3y, 2x1 plus 3x2 equal to 7. 5x1 plus 7x2 equal to 10. You know how to solve for the x1 and x2, right? Right? That's the linear equation. Two unknown and two equation. Finite solution, right? Right? If I ask you solve these things, 2x1, 3x2, 5x3 equal to 7, 7x1, 10x2, 17x3 equal to 20. How can you solve this? How can you solve these two equations? Because there are three unknown and two equations. So there is a infinitely many solutions, right? Why infinitely many solutions? Suppose x1 equal to 10. I said suppose x1 equal to 10, right? If x1 equal to 10, I plug, then I will have the solution for the x1 and x2. You said no, x1 equal to 20. Then x2 and x3 will have a different solution, right? So that is why that is called the infinitely many solution. Depends on what is you assume for the x1 or x3. One of the value you have to assume, right? Clear. So you successfully answer how to solve this type of equations and what will be the solution for this type of equation, right? Now I want to ask you a third question. Suppose you have these things 2x1, 3x2 equal to 7, 5x1, 7x2 equal to 9, 20x1 plus 40x2 equal to 10, 5x1, 10x2 equal to 7, and 9x1 plus 11x2 equal to 10. How many equations now? 5. How many unknown? How can I solve this? Is there any way to solve this? Do you understand? I want to use each equation. I want to use all of this equation to solve the unknown of x1 and x2. How can you solve this? Okay? How can we solve this? So there is no algebraic magic to solve this problem. So that is why calculus is needed. Okay? So Galton give a solution of this type of problem. Okay? So how? Take a look. Now take a look at the equation. I have written here y1 equal to beta 0 plus beta 1 x1 plus e1. y2 equal to beta 0 plus beta 2 x2 beta 1 e2, e1 and e2. And then y3 equal to beta 0 plus beta 2 x3, this is beta 1, this is beta 0 beta 1, x3 plus e3. And then we will stop n observation yn beta 0 plus beta 1 x n plus en. I have 10 response variable and 10 values of the response variable corresponding to the 10 values of the predictor variable, right? For example, if I want to write it like this way, this is my x1, which is equal to height, which is equal to height. And this is my y, which is equal to weight, right? So I have a height in here. Suppose this is 4.9. I will have a weight in there. I have a height in there. I have a height in there. I have 10 values. This is the y equal to weight, x equal to height. Now, how can I estimate beta 0 and beta 1? Like the way I said, how can I get x1 and x2? Are you understanding? This is all linear equations, right? This is all linear equation. This is also all linear, right? This is all linear, same format as it is, right? Exactly same format as it is. Clear, right? So Galton said that yi equal to beta 0 plus beta 1 xi plus ei. He said purpose is to minimize the error. This is my error term. Beta 0, beta 1, xi. Everyone is okay with that? This is the error term, right? So I can take the square of the error term, right? I take the square of the error term, then I make the sum of the square. See. I take the square term and then make the sum of the square. So now this is the sum of square, right? Sum of square of error, right? The minimum the sum of square of error, the maximum the production is, right? We have to minimize these things, right? So how can you minimize these things? If first derivative equal to 0 and second derivative is positive, then you have a minimum. And first derivative is 0, second derivative is negative, then it will be maximum. For example, suppose this is your case, right? See, this is the way slope, and there is no slope in here, right? There is no slope in here. If I put you in there, you will sit there. But if I put you in there, you will fall down, right? If I put you in there, you will stay there. But if I put it in there, you will fall, right? Right. And then after first order derivative, here 0, there is no slope, there is no rate. Right. More explicitly, if I want to explain you what is rate, suppose this is the 10th floor. Okay. So this could be the starting point, 10th floor. Our target is to reach the 10th floor, right? So this is the starting point. I can reach there like that way, right? And someone can reach there that way. This is faster, right? Rate is faster in here. Someone can reach there like this way, right? That is the faster way, right? Rate. That is why I call the slope. And slope is coming from where? The rate or change of rate, all of this is calculus. How? Let me spend 2-3 minutes on there. So this is a slower rate to reach 10th floor. This is the faster, this is way faster. Okay. So then if this is the way you can reach there, the faster rate, slower rate, more slower, then you already reach there, no more slope in there. And then second derivative, when you, if this is the 0, second derivative is going down, right? Slope. Are you seeing? So that is why if you are given a function to find the maximum of minimum, first derivative equal to 0 and second derivative positive. So that means you have a minimum, and second derivative negative, because in here second derivative is going down, so negative. So that means you have a maximum. This is the maximum point of this function. That is the maximum point of this function. Clear, right? Okay. Now I want to give you, what do you mean by dy dx? What is the meaning of dy divided by dx? Okay. This is called the derivative, right? Also called the change of rate. Also called the change of rate. Change of rate is also called the rate. How? I want to give you a very beautiful example so that you will never forget these things. If someone in your life asks you what does dy dx means? Dy dx means change of rate or rate itself. Take a look at that realistic example. I'm coming to the derivation realistic example. 10 people yesterday made $80. 10 people yesterday made $80, right? Right? Same 10 people today made $100. So this is the rate for the per person today minus rate for the per person yesterday, right? So this is the change of rate, right? Right? 10 persons have made $100 today. Same 10% made $80 yesterday. So that means this is the per person rate, subtract one from another. So this is the change of rate for per person, right? Now can I write like this way? This is 10 and this is 100 minus 80. Okay. Now take a look at this. Can I write like this way? F of x plus h minus f of x divided by x plus h minus x. X was yesterday, x plus h is today. Right? And then yesterday minus today. So I want to make a little change in here. So this got cancelled out, right? These got cancelled out. So now cancelled out, what you have? You have h f of x plus h minus f of x. And what Newton and Leibniz they did, for any discrete number, we can compute everything and see visually everything. But if it is a continuous scale, every second, every millisecond, how can I do that? Do you understand? Every second, every millisecond change of rate. For example, if you take a look at the stock price, every second it is changing, right? This Elon Musk make a tweet, went up. Elon Musk make a tweet, BYD, Chinese car company, is taking over the world, and they lost immediately $10 billion. Do you understand? So every second we want to see the change of rate in the continuous scale. So change of rate in discrete scale, even in the 8th grade, 9th grade, 10th grade student will understand. Discrete scale. For example, any 10th grade students, if you ask, they will understand. But they will have problem what? They will have a problem when I put their limit, and then if I put here h goes to 0, then they will say that why are you doing these things? I am doing these things. I want to find the change of rate every second, every millisecond. Okay. And then if you put a functional value in here, and then if you do some algebraic calculation and plug h equal to 0, then it will be the change of rate in the continuous scale. So dy divided by dx or ddx of y. Some people might argue with you, dy divided by dx, you cannot tell. If this is what some people tell you, then bring him to me. Okay. It could be said dy, some people say d, some people say the ddx of y. So change of y with respect to x. So this is what they are saying. But they have a separate entity. They have a numerator and denominator, right? Are you seeing numerator and denominator, right? They have a separate entity. If they do not have a separate entity, then you cannot do all operations. Okay. So dy divided by dx, if you say, there will not be any issue. So that is the way you come into an existence. This is what finally, after plugging those things, you will get some value in there. That is called the change of rate. So the slope that you are seeing there, where is that one? This one is called the slope, change of rate. More specifically, if x value will go up, usually y value will go up unless beta is negative. In such a cases, x value will go up, y value will go down. Depending on the sign of the beta 1 value, the y value move in same directions or opposite direction with respect to x. Okay. So now I give you what is rate and what is minimum, maximum, and what is dy, ddx of y. Okay, what is ddx of y? Now I want to find the solutions for that one. This is sum of e I square is written as n, I goes 1 to n, yi beta 0 minus beta 1 xi square, which is known as the sum of square of error. So now I want to differentiate these. With respect to beta 0, and let's see what I will get. If I differentiate this with respect to beta 0, I get 2 I got 1 to n yi minus beta 0 beta 1 xi, and then I got here with respect to beta 0, I got here minus 1. So that means I am getting here minus 2 sum of n I goes 1 to 1 y minus beta 0 minus beta 1 xi. Do you understand these things? No?
Partial differentiation.
I am differentiating these with respect to beta 0. So this is a square, that 2 comes in here. Okay? And these summations, I have to differentiate. I have to differentiate entire part in here. If I differentiate this with respect to beta 0, it is 0. If I differentiate this is equal to minus 1. If I differentiate this with respect to beta 0, then it is 0. So that means we have a minus 1. You got it or not? More explanation needed? Okay. So now I got a one equation is this. Now if you differentiate this with respect to beta 1, then you got sum of I beta 0 beta 1 xi, and then you got the just xi. So you are getting here minus 2 sum of I goes 1 to n xi yi beta 0 minus beta xi. This is what you got. I am differentiating sum of squares of error with respect to beta 0 and beta 1. This is the two equations I need. One thing you should remember, your homework problem will be completely applied. I'll give you real data and some code will be given. You are allowed to do the like computational homework, and your exam will be conceptual. Okay, your exam will be conceptual. You have to understand when to use what type of model. Understand? So mathematical derivation will not be in the exam, but I have to convince you how this model coming to an existence. That's the way American education system is based on. Professor come, they discuss all the theory, history, development, and real life example, and then you will do the homework like that way. So I have two equations. From these two equations, I want to find the solution. Why did I say here 0? This equation equal to first order derivative. I am considering first order derivative here. There is no slope. There is no rate. Rate is 0 in there. There is no slope in this case. So if I plug here 0, then I can get the solution. Understand? Why I put there 0? If someone asks you the question is that first order derivative 0 means there is no rate, nothing is in there. Okay. So we need to solve it. So that is after doing the first order derivative, I am plugging that equation equal to 0 in order to find the solutions of the unknown constant beta 0 and beta 1. Okay, come from the first equations. Suppose this is 1, that is 2. These are the 1 and 2 equations. From 1, what we get? From 1 we get sum of yi minus n beta 0 minus beta 1 sum of xi equal to 0. So there is a 0. So negative 2 is gone there. 0 in the top, negative 2 in the denominator, it is gone. So and then minus sign will also be gone. And then there is sum of yi and sum of yi and beta 0 equal to n beta, and this is the things I have in there. So from there I can write sum of yi equal to n y bar n beta 0 and beta 1 and x bar equal to 0. Why? Because x bar equal to sum of xi over n. So n x bar equal to sum of xy. This is the things I have considered. When I plug there n x bar, that is sum of xi. This is sum of xi, okay? So this is an x bar that you are seeing there. That n x bar, sum of x, this is coming actually from there. Okay? Clear, right? So I have a one equation that could be written as that could be written as y bar minus beta 1 x bar equal to beta 0. From there I can write like this. From there I can write like that. Clear? And there is how many n? 3n, right? So if you divide by n in both sides, n gone, right? Are you okay, gentlemen? So this is a n and n. If you divide by n, then one n is gone. Okay? So what you have in here, you have beta 0 equal to y bar minus beta 1 x bar. This is what you have. Now from 2, what did you get? From 2 you will get minus sum of xi yi minus beta 0 sum of xi and then minus beta 1 sum of xi square equal to 0 from 2. Negative, because right side has a 0, I just divide both sides by negative 2. We have this thing, sum of xi yi, sum of beta 0, and then minus beta 1 sum of xi square. Okay? Purpose is to find now beta 1. Okay. In order to find the beta 1, if I write like this way, beta 1 sum of xi square equal to could be written as sum of xi yi minus beta 0 sum of xi. That is the way I can write like this way. Sum of xi, one side I took, otherwise so I get this one. Now I want to put there sum of xi yi as it is, and then I want to put beta 0's value in here, which is equal to y bar minus beta 1 x bar. This is the beta 0's value. I plug it in there. From there, okay, and then this is the things I can write here, n x bar. N x bar I can write in there. After writing these things, what I can get? Sum of xi yi and then n x bar y bar and then plus I got here beta 1 and x bar square. N x bar y bar and x bar y bar, this times that equal to plus beta 1. Now take a look what I am doing. If I bring out that beta 1 sum of xi square beta 1 and x bar square, then what I have? Sum of xi yi n bar y bar. So now I can write here beta 1 as a common. I can write here sum of xi square and x bar square, and then here I have sum of xi yi and x bar y bar. Finally, this beta 1 is written as sum of xi, yi, and x bar, y bar, sum of xi square and x bar square. So this is my beta 1, and this is my beta 0, which is equal to y bar, beta 1, x bar. Now I want to give you some explanation. I want to spend 1 or 2 minutes in here. Everyone ready? Okay. Take a look. My purpose, how did I formulate the question to you so that you can understand? I said certain kind of system of linear equation and asked you question. You appropriately answered the question. Then I ask you challenging questions. I want to solve for x and y by using all of these informations. These 5 equations I want to use in order to find the value of x1 and x2, right? This is the question. This x1 and x2. So I wrote this equation in this format. Take the error sum of square and do the first order derivative and equate it equal to 0 by following the principles of no rate or no change of rate. I finally come into a decisions where all data points is being used. Take a look. In this case, sum of xi and yi, all data point used, right? All x and y are used, and x bar and y bar. In order to compute mean, you have to use all data points. All data point has been used in order to compute beta 0 and beta 1. Okay? So Galton derived these things. It has a name. It has a name, least square method. Least square. What is least square? Least squares of error. Didn't I say the minimum, the error, the maximum, the production? So why they said least square? They took the sum of square and then they try to minimize that error. So that is a least square of error. Clear, right? So anytime any mathematics is working, some talented people sacrificing their personal life, family life, marriage life, they develop all of these things for us. Okay? Right? Okay. So you are convinced how to solve this problem. Now, next step. This is the simple linear regressions. But how can I solve the linear regressions when this is like this? Beta 1, x, 1i, beta 2, x, 2i, and then all the way beta 3, x, beta k, x ki plus epsilon I. Okay? How can I do that? Remember, if I write I equal to 1 to 3, y1 and then y2 and then all the way yn, right the way I have written, then I can write here beta 0 and then beta 1 x 1 1 and then beta 2 x 2 1 and then all the way beta k x k1 and then epsilon 1 and then finally beta 0 beta 1 x 1n beta 2 x 2n and then beta k x kn and then en. Right? So now these things as a column vector, you can write it as a y. Understand? These things you can write as a column vector y. These x's you can write as a matrix of x. Okay? And these betas you can write as a beta, and then you can write it like this way. For example, y equal to what? Let me write it here so that in your future life, you will never forget these things. Right? And then x equal to what? 1, x11, x21, x k1, 1, x22, 21, x22, xk 2 dot dot 1 x and 1 x and 2, then x 1 2 1 2 2 x um 1 2 2 2 k2. That's it. So this is 1 n, this is 2 n, this is kn. Right? Right? And then beta equal to, you can write here beta 1, beta 2, all the way, beta 0, beta 1, all the way, beta k. Right? So now, if you plug it in there, these times that, you will get first row, these times that you will get second row, this time that you will get the last row. Right? Are you understanding? So what you have for the multiple linear regression model, you have y equal to x beta minus x beta plus e. So this could be written as e equal to y minus x beta, right? Arrow term. This is called the arrow term.
We eliminate beta. Why?
No, why? Here is the beta 0. Beta 0, beta 1, beta 2. This is the beta 0.
Here we put it in the equation y equal to x.
This beta is representing all betas. This beta is representing all betas.
Oh,
Clear, right? In order to find shortcut beautiful solution by using matrix algebra approach, we are going that way. So without giving the explanation of how come into an existence of the simple and multiple linear regressions, if I directly jump in there, then you will have a problem. So that's the way I'm building the foundation. Okay, so now if I write like this, then we have something like this. Transpose. If I take a transpose on there, this is that. This equal to this, and there is a transpose in there. Okay. So now if you multiply what you have, y transpose y, and then y transpose x beta, then beta x y, and then plus beta transpose x beta. Matrix multiplication. This is known as the matrix multiplication, okay? Clear? These two terms are the same term. These two terms are known as the scalar. Scalar means what? Only one quantity. Okay, only one quantity. For example, let me show you. Let me give you the explanation of these terms. Suppose y prime x and beta. Okay, y prime has two values, suppose 2 and 4. This is the value for the y prime. X value has 4 value, 1, 2, 3, 4. 1, 2, 3, 4. Okay, beta has suppose 3 and 6. So this is my y prime, this is my x, and this is my beta. Okay, suppose I have said that these two quantity are scalar. I have to prove it, right? I have to convince you what is scalar. Scalar means only one number. If you multiply these things, you will end up with only one number. For example, this times that, here is a 2 and 12. So we have 14 in here, right? Right? This times that equal to 14. And that times they equal to 4 and 16. So we have a 20 there. And then 3 and 6. Do you agree or not? Matrix multiplication, right? Now I want to multiply this and that. What we have? 40, 42 and 120. 162, right? Now let us do it in other way. Beta prime, x prime, y. So beta prime equal to what? 3 and 6. Here it is column matrix. Now beta prime will be row matrix. Okay, come in there. X. So 1 and 2, 3 and 4. Okay, and then that it will be y equal to 2 and 4. Okay, if you multiply these things, you will end up with 162. Only one number, right? Only one number. That is called the scalar. I am not multiplying these things. I'm just showing that. So these two are the same. As these two are the same, we have to write it like this way. We want to write it y prime y minus 2 y prime x beta plus beta x prime x beta. Clear, right? As these are the same thing, so I just may say that this is a two term. Now we had what? We had this. Now if you differentiate this with respect to beta, you will get what? 2 what was the value as in there? Let me see. This is the formula. So that is the formula. Is this the formula? I think that is the formula. Let me see. Beta x prime y. So I should better go like that way. If I go by that route, then I would have this format. Otherwise, I have to differentiate it in this format. Okay. Either way, it is fine. So either you can differentiate with respect to beta prime or beta. As I did these things, it will change in this format. It will change. But anyway, so if you write like this way, in this case, it will also work. So let me write it 2 beta. Let me write it this format, draw and draw. Let me write it in this format. 2 beta prime x prime y. In that way, if you write and differentiate this, now your there will be 2, then it will be x prime y. Here is the minus, and in this case, you will get 2 x prime x beta equal to 0. First order derivative equal to 0. Okay, so from there you can write in here, x prime x beta equal to x prime y. Okay, from there you can write. Now if you multiply both sides by x prime x inverse x prime x times beta x prime x inverse x prime y, then this is cancelled out. So you have beta hat equal to x prime x inverse x prime y. So that is the solution of the betas. Clear? So you have seen from the simple linear regression, beta 0 equal to y bar minus beta 1 hat x bar, and then beta 1 hat equal to, you have seen, sum of xi square. Let me check, I forgot after derivation. Somewhere nx bar and x bar square, sum of xi, yi, and x bar square, y bar square, or nx bar, y bar. Let me see, nx bar, y bar, not square. Okay. So this is not true. This is not true. Good. So for the simple linear regression model, this is the solution. For multiple linear regression model, the solution is beta hat equal to x prime x inverse x prime y. Okay? You know the transpose of a matrix, right? Those things you already know, right? Clear, right? So past 50 minutes, I spent to convince you how linear regression come into an existence and how it extends to multiple linear regressions. Okay? Clear?
Why do you write -2 beta transpose in the first line?
This one? This one?
Oh,
This one?
yeah.
This one? Okay.
Same.
That is why I convince you these things are the same. That thing is same. That is why I took an example in here. Y prime x beta, and then I take beta prime x prime y. I multiply those things, come up with the same thing. 162, 162. That means scalar. In derivative one?
Second one,
Here. Because there are two beta, right? One beta gone.
if we derivative one beta, how will be?
So that means if you if this is your square, if you do these things ddx, then it is 2x, right?
It's beta transpose and one is beta transpose, one is beta.
Here is one beta transpose and here is beta, right?
Yeah.
So you said that one has the transpose and one has the beta, right?
So
But listen, take a look at that. Beta transpose has this format: beta 0, beta 1, and beta k, right? And beta has this format. One is row vector, another one is column vector, right? Beta 0, beta 1, beta k, right? Now if you multiply, then you are getting what? Beta 0 square, beta 1 square, up to beta k square. So each and everything will have a beta, no transpose is in there. So when you take the derivative, it is actually taking over the betas. So there is a calculus known as the gradient calculus, like the vector calculus. Okay. So those things, do you understand how these things working in here? This is a beta prime, but when you plug the beta prime, that does not have a prime. That has just the betas. Clear, right? Clear? Okay. Any question? Still you have a question? No? Okay. Now I have to tell you, now I have given you mathematical background. Down the road, someone will ask you, this is the estimate, how this come into an existence, that is the way come into an existence, okay? Clear, right? Now, question number, when to use simple linear regression and multiple linear regression?
So, Professor, we have done this multiple linear regression.
Yeah, this is the multiple linear regression. So take a look at that. I wrote an equation, right? I wrote this equation, right? That is the multiple linear regression model. Right? How can I estimate the betas in here? That is the estimates of the betas. That is the estimates of the beta. This X is a big matrix of all the explanatory variable. And it has a transpose over there. This is another X. This is equal to that. Okay. So this multiply that, you will get a matrix of like this. And then you will have to take the inverse of that matrix. You will multiply this. After multiply these things, you will get a matrix like this. Okay. Right? And then you have a yi. Y is just this. Then when you multiply this with that, you will get one value. Multiply this with that, you will get second value. Multiply this with that, you will get the last value. So this is the estimate of the beta 0. This is beta 1. This is beta k. Are you understanding? Online people, are you understanding? Charity, are you okay? Oh, Lade. Are you okay?
Yes.
African people's name is very difficult. Last 3 semesters I am teaching in here, I am struggling by calling their name. Except Charity. Charity, your first name is very easy. Okay? You understand, right?
Thank you.
Okay. So now I want to tell you when to use this regression. When to use this regression. Listen carefully. If you want to use this regression, first of all, y must be continuous or quantitative. Continuous. Okay? If your y is not continuous, if your y is a count data, number of accident, number of phone call, you cannot use this. Number of children born from per women. You want to predict number of children born from women by looking at the women education, women age, women race, women working status, women race, geographic locations. You cannot use this regression. Simple multiple regression you cannot use. You understand? Y must be continuous or quantitative. That is one. Number 2, Y must follow normal distribution. Y must follow normal distribution. So it has a distribution format. Y must have this probability format. Okay? This probability format. Clear, right? 2 conditions. Y must be continuous. Y must follow normal distributions. Number 3. How can you say that it is not following? Good question. Can anyone ask you? You are given a data. Suppose you are given a height and you are asked to predict the height from their weight, from their soft drink habit, how many soft drink you eat each day. You want to predict couple of variables. So what you will do, you will go and plot the y in a format of histogram. If your histogram, after getting the histogram, suppose this is your histogram, your classmate asks, how should I know y follow normal distributions? Suppose your y equal to height which you want to predict. So you want to predict height from the multiple linear regression model, draw a histogram of y, if and then top middle point of each bar, if you like this way, if you see it is a symmetric, then you consider that this is normal. Understand? So that means this is the point, 50% of is in the left, okay, and then 50% of that is in the right? Approximately normal, you can say that. Number one, histogram approach. Number one, you take the height, you do the histogram looks symmetric, you say that, well, my response variable follow normal distributions, approximately normal. I will go with the multiple linear regression model to predict the height from a number of covariate like weight, drinking habit of soda, eating habit of first food, second food, third food, all other food, okay, exercise habit, all of these things. So second approach is Shapiro will test. Shapiro will test to check normality. Okay, Shapiro will test. If you conduct this on the y response variable, then they will give you p-value. If a p-value less than 0.5, do not use it. Okay, he actually asks a good question. If p-value greater than 0.5, then y follow normal distributions. Understand? So now further questions, suppose p-value less than 0, y does not follow normal distribution. What should I do? You understand the question? Y does not follow normal distribution. Histogram and Shapiro will test does not look like normal. What can I do? Third approach, excuse me, apply log transformation on your response variable. Okay, apply log transformations and then construct histogram, and Shapiro will test, check whether now it is normal. Understand? He asked a very good question. Suppose how can I know y follow normal distributions or not? You will do histogram construction for your response variable, or Shapiro will test. If histogram looks like skewed to the right or skewed to the left, and Shapiro will test p-value less than 0.5, then it is not following normal distributions. Go for the log transformations of the response variable, and then construct histogram and conduct Shapiro will test to check whether histogram and Shapiro will test p-value is less than greater than 0.5 on the log scale, as well as histogram on the log scale is normal or not. If log transformation does not work, final approach. Log transformation does not work, final approach. Apply Box-Cox transformation. Okay. Box-Cox transformations on what? On what? On what variable? On what variable? Box-Cox transformation. What variable? Response variable. Y variable. You said Y, right? Okay, I did not hear. I don't know why you are afraid of speaking loud. I'm not gonna beat you, okay? I'm not gonna punch in you, Joe, if you wrong something. So speak loud. Understand, right? Box-Cox transformation, like almost sure that it will be normal. Very strong. Let me tell you a little history. R.A. Fisher is the father of statistics. R.A. Fisher. He developed a lot of statistical. Originally, he was a genetics and biology professor, R.A. Fisher. Okay. So Box married the daughter of R.A. Fisher. Okay. Box married the daughter of R.A. Fisher. When I read any article, anything, I want to find their background. I want to know their history, when it happened, how did it come into an existence. Okay. See, linear equations was developed more than 2,300 years ago. The geometry Euclid who developed all of these things. But regression, it is just 220 years ago, right? 1805, 1905, 2005, 219 years ago. And rest of the regressions that we are going to discuss, all of these developed in past centuries. One regression that I am going to discuss that was developed in 2007. Okay, so statistics is relatively very nascent, like it is even not like 100 years old in many American university. First statistics department was established in Britain in 1905, and USA first statistics department was established in George Washington University in 1932 or 33, something like that. Okay. Clear. I'm not done yet. Many important thing I have to discuss in here. That is the foundation. So now let me discuss you, because you need to understand how the things work behind the scene. Take a look. I said this, right? Yi equal to beta 0 plus beta 1 x I plus epsilon I. This is the simple linear regression model, right? Simple linear regression. What did I say? Y, that means dependent variable must follow normal distribution. How can this possible? Okay, in these things, this is fixed. It is explanatory variable or predictor variable or regressor or independent variable, but this is fixed. Okay, that is random. That is random. It has a distribution. Y is a random and it has a distribution. Probability distribution. How? Didn't I say it should follow the normal distribution? How? I want to show you visually how that distribution exists. Are you understanding? Okay. Take a look at that. That is why this model is called the fixed effect model. This model is called the fixed effect model. Fixed effect means xi's are fixed. How? Okay. Then there is a random effect model, which I'm going to discuss when I discuss linear mixed effect model. Understand? So now let me explain you. These visualizations is very important for you to understand. I want to predict Y based on height xi. I want to predict Y, which is weight. Okay. I want to predict Y, which is weight based on height. I said X is my height, Y is my weight, and I also said that X is fixed. How it is fixed? You need to understand. Without looking at the graph, you do not understand. Suppose I want to take a height in here, which is equal to 3 feet. 3 feet height I take, okay. If I take 3 feet height in here, if I take 3 feet height in here, I can construct a histogram in here. For example, like after constructing histogram like this, clear, right? This is height, 3 feet of height. Let me be very careful and and these are the weight you are saying. These are the weight. I fix 3 feet height. Okay. I pick a 3 feet high American boy. His weight will be what? Maybe 40 pounds. Okay. I pick a 3 feet high boy from Africa. His weight will be 60 pounds. I pick a 3 feet high girl. Her weight will be 35 pounds. So when I fix one height, I'm getting the distributions of the weight for different people, right? Are you understanding? So now I want to say that this is 20 to 30 pound, 30 to 40, 40 to 50, 50 to 60, 60 to 70, 70 to 80, 80 to 90, 90 to 100. I know that is too much, right? And this is the what? Number of persons. 20 to 30, how many persons? There are, suppose 10%. And then 30 to 40, how many percent? Suppose there are 20%. Understand? So I got a distributions of the weight for a fixed height that is normal. Are you understanding? Are you understanding? And then I got their mean is in there. Normal distribution, it has a mean, right? I am constructing how linear regression is constructed. Okay. Now I want to move to the height 4 feet now. 4 feet high. Clear? I now move to the height of a 4 feet. Now, again 4 feet, I can get another distributions like that. I did not construct here any histogram. I just put the smooth curve by adding the top middle point. I got another in here, and this is the mean, right? Are you understanding?
Yeah.
So now if I move to the 5 feet, then I will get another distributions in here. I can get like curve like this, which is like this. Then this is the curve, right? That is the regression line. That is the regression line. So this is regression is the average regression line. This is the line that we see y equal to x beta plus, sorry. This is what more specifically I write y expected value of y equal to beta 0 plus beta 1 x I. That is the regression line. So we assume for the fixed values of x, there is a distribution of y. For a fixed value of height, there are many people with different weight. That weight will have a distributions. I am picking the mean of that distributions and fit the regression line. So it is the assumption that when we are fitting this line is a average regression. Okay. Do you understand? Do you understand this graph, how this graph works? So for a particular height, there is a distribution of weight. There is a distribution of weight for different height, and then I am fitting the line on the average. So this line is going through the average. This is the average. This line is going through the average. Then again you take the 6 feet. Then you will get another one in there. So you understand why it is fixed effect, right? Even it is not a predictor variable, regressor variable, independent variable, okay, explanatory variable, but these axes are fixed. Each of these axes you have a distribution of y. That is why in this model it is said, let me write it, yi equal to beta 0 plus beta 1 xi plus epsilon I. When you take the expected value of yi, you are getting beta 0 plus beta 1 xi, and then expected value of ei. So you put there beta 0 plus beta 1 xi, and that is equal to 0 because error term equal to 0. So that means expected value of yi equal to beta 0 plus beta 1 xi.
When we take estimated value of y, I tend to take estimated value of x.
Yeah. Can anyone of you ask his question? Your classmate asks, when I take the expected value in there, why I did not operate expected value on beta 0, beta 1, x1? Can anyone of you tell me?
Y is the response variable x.
So then why I am not taking x in there? Why I am not taking expected value on there? His question is why expected value of beta 0 or expected value of beta 1 or expected value of xi, why I did not take it in there? Anyone from online? Shafali? Charity? Anyone else? Okay, expected value of 5 equal to what? 5. Why? 5 is a fixed, constant.
It's constant.
So beta 0 is a constant. Beta 1 is a constant. And xo is a fixed that I just mentioned.
Yeah. Thank you.
No, that is a good thing. If you ask me questions, so that means that is a good question. You know, when top people call good conferences, you will go there. Top people asking top other people, and then they're hesitant to ask the question. So they politely ask, "Can I ask you a dumb question?" So the guy who is presenting, he elegantly answer, "No question is a dumb question." Because the person who is presenting the thing, other person may not understand. Let me tell you one very important thing. It happened in our Dhaka University in 1951. 1951. R.A. Fisher, he went to Dhaka University and he was giving a presentation. And the name is Kazi Mutahar Hussain. Kazi Mutahar Hussain. He was the founder of statistics department in Bangladesh, 1950 and 51. So R.A. Fisher was traveling from England to Dhaka University around 50 and 51. And then Kazi Mutahar Hussain is asking, I don't know how this parameter come into and these estimations, these things, around a lot of people. So R.A. Fisher says, oh, that is very simple, like this way. Very simple 2 or 3 lines. And then he said, so R.A. Fisher said that don't be shame. Sometimes very simple thing will not catch to your head. There are a lot of people was in there. So when the old statistician from our country, they gather, they say this gossip, they said that these things, and then they want to legalize that. Sometimes very simple thing might not come to your head. It's happened. And later, when Kazi Mutar Hossain write his PhD dissertation under his supervision, and then the R.A. Fisher wrote, what Kazi Mutar Hossain did, I cannot did this. Kazi Mutar Hossain developed a design of experiment which is known as the Hossain chain. Okay. So Kazi Mutar Hossain is not known rest of the world like the way R.A. Fisher known. R.A. Fisher, every statistician know R.A. Fisher. Who took a course, R.A. Fisher's like statistics. So sometimes those things come. So your classmate asked why I did not take expectations over there. Because beta 0, beta 1 and X size are fixed. So I do not need to take any expectation over there, okay? So you understand, this is a fixed model and how normality assumptions it applied. See, I am for a fixed height, I am assuming a normal distributions for Y, right? For a fixed height, I am assuming a normal distributions for Y, for weight. If this is not normal, Y is not normal, then what are you going to do? You have to apply log transformations or Box-Cox transformations. Understand? So now tell me what is the variance of A? What is the variance of 5?
Oh, 0.
0, right? So 5 variance means variability, right? What is the formula for the variance? Variance formula is this, xi minus x bar square, right? So 5 is only one number and 5 is xi equal to 5, x bar itself equal to 5, right? So that means 5 minus 5 equal to 0. So there is no variability. So that is why this is equal to 0. Okay. So this is the all discussion about simple and multiple regressions. Now you know how these simple and multiple linear regressions come into an existence. There was a linear equation which has been existing more than 300 years. Thus geometry was developed by the founder or father of geometry known as the Euclid, a Greek mathematician, philosopher who born in Alexandria, Egypt, but is just 220 years ago. Simple regression come into an existence by Galton. Okay, and then that is the extension of the multiple linear regression model, and and I have given some assumptions. What does Y, E, X stands for, how to estimate the parameter. These are the things I have given. Okay, you have a question?
When we estimate the standard deviation of sigma square, we sometimes take n minus 1 and sometimes we take n. Why?
Okay, so this is the xi minus mu. This is called the population standard deviation. Okay. Now suppose WIU has how many students? WIU 6,000, right? Suppose 6,000 students. If I want to find the mean age of the WI students, mean age, what is the formula? All 6,000 students, I have to apply this formula, right? Right? Xi stands for the age. This is the age, mean. But suppose I want to take a sample of 500. Then mean age equal to what? Mean age equal to sum of xi over 500, right? Clear, right? So the formula is same for the mean computation. Why formula is different? Why formula is different for variance, right? Question? No question. Okay. Now, suppose WI has 6,000 students and I want to compute the variance for this 6,000. So formula is 1 over n sum of xi minus, I want to put here this capital X bar square. Okay. Now I want to take a sample of 500 and then variance of sample is 1 over n minus 1 sum of xi minus this small x bar. Why this? Statistics has certain properties after computing, after doing estimations. So what are the properties? The properties is unbiasedness. Unbiasedness. Okay. Then this is number one. Number two, call the consistency. Consistency. So, four properties: unbiasedness, consistency, sufficiency. There is another one. Unbiasedness, consistency, sufficiency. Yeah, we can also do the completeness one. But these are the main. So this has a notation sigma square. This has a notation S square. Okay. So in order to find the unbiased estimate of the populations, this is mathematically proved that expectation of S square equal to sigma square. This is mathematically proved. Understand? This is mathematically proved. So that is why it is written like that way. And also once you compute another thing, once you compute, in order to compute variance, you have to compute mean, right? You have to compute mean. So by using the data, you are computing the mean. So you are losing the freedomness. In one freedomness you are losing. It is mathematically proved. Then it could be, for example, I can show you like freedomness, like 5-6 data point. If I compute these things, then you lose the freedomness for, because all the data you use to compute this X bar. So that is why you're losing one. Maybe next time I will give you more concrete example, more realistic. Right now it is not coming, it is not hitting my head. Something coming obscure, but I don't want to write that obscure thing. But I will give you more clear example, okay? But the main purpose is that S square is the unbiased estimator. Sample variance, this formula is the unbiased estimator of that. If you replace this by n, then it is not unbiased. This, your question is, here is n, why it is not n, why it is n minus 1? If you replace this by the n, 1 over n minus 1 will be replaced by 1 over n, then it is not a unbiased estimator. Understand? It is coming from unbiasedness, and I will give more explanation for that. Okay, I'll give more explanation for that. And what else? I think I discussed enough about graphical presentations, why it is fixed model, why this response variable, all of this. Okay. Now I think you can take 5 minutes or 7 minutes break. then I will start discussing another topic, okay?